At the end of this video, you should be able to explain VSEPR theory and predict the shapes of molecules or polyatomic ions using VSEPR theory. Chapter 6, Section 5, Molecular Geometry. The properties of molecules depend not only on the bonding of the atoms, but also on molecular geometry, which is the three-dimensional arrangement of a molecule's atoms in space. The polarity of each bond, along with the geometry of the molecule, determines molecular polarity, or the uneven distribution of molecular charge. As you will read, molecular polarity strongly influences the forces that act between molecules in liquids and solids. A chemical formula reveals little information about a molecule's geometry. After performing many tests designed to reveal the shapes of various molecules, chemists developed two different, equally successful theories to explain certain aspects of their findings. One theory accounts for molecular bond angles. The other is used to describe the orbitals that contain the valence electrons of a molecule's atoms. VSEPR theory. As is shown in figure 6-20 on page 183 of your text, or on the screen now, diatomic molecules, like those of hydrogen, H2, and hydrogen chloride, HCl, must be linear because they consist of only two atoms. To predict the geometries of more complicated molecules, one must consider the locations of all electron pairs surrounding the bonded atoms. This is the basis of VSEPR theory. The abbreviation VSEPR, VSEPR, stands for valence shell electron pair repulsion, referring to the repulsion between pairs of valence electrons of the atoms in a molecule. VSEPR theory states that repulsion between the sets of valence level electrons surrounding an atom causes these sets to be oriented as far apart as possible. How does the assumption that electrons and molecules repel each other account for molecular shapes? For now, let us consider only molecules with no unshared valence electron pairs on the central atom. Let's examine the simple molecule BeF2, beryllium fluoride. Recall that beryllium does not follow the octet rule. The beryllium atom forms a covalent bond with each fluorine atom. It is surrounded by only the two electron pairs that it shares with the fluorine atoms. According to VSEPR, the shared pairs are oriented as far away from each other as is possible. As is shown in figure 6-21a on page 184 of your text, or on the screen now, the distance between electron pairs is maximized if the bonds to fluorine are on opposite sides of the beryllium atom, 180 degrees apart. Thus, all three atoms lie on a straight line. The molecule is linear. If we represent the central atom in a molecule by the letter A, and we represent the atoms bonded to the central atom by the letter B, then according to VSEPR, beryllium fluoride, BeF2, is an example of an AB2 molecule, which is linear. Can you determine what an AB3 molecule looks like? The three A to B bonds stay farthest apart by pointing to the corners of an equilateral triangle, giving 120-degree angles between the bonds. This trigonal or trigonal planar geometry is shown in figure 6-21b for the AB3 molecule boron trifluoride, BF3. Unlike AB2 and AB3 molecules, the central atoms in AB4 molecules follow the octet rule by sharing 4 electron pairs with B atoms. The distance between electron pairs is maximized if each AB bond points to one of 4 corners of a tetrahedron. This geometry is shown in figure 6-21c for the AB4 molecule methane, which is CH4. The same figure shows that in a tetrahedral molecule, each of the bond angles formed by the A atom to any 2 of the B atoms is equal to 109.5. The shapes of various molecules are summarized in Table 6-5 on page 186 of your text or on the screen now. B can represent a single type of atom, a group of identical atoms, or a group of different atoms on the same molecule. The shape of the molecule will still be based on the forms given in the table. However, different sizes of B groups distort the bond angles, making some bond angles larger or smaller than those given in the table. VSEPR and unshared electron pairs. Ammonia, NH3, and water, H2O, are examples of molecules in which the central atom has both shared and unshared electron pairs. See Table 6-5 on page 186 of your text for the Lewis structures. How does VSEPR theory account for the geometries of these molecules? The Lewis structure of ammonia shows that in addition to the 3 electron pairs it shares with the 3 hydrogen atoms, the central nitrogen atom has 1 unshared pair of electrons. VSEPR theory postulates that the lone pair occupies space around the nitrogen atom just as the bonding pairs do. Thus, in an AB4 molecule, the electron pairs maximize their separation by assuming the 4 corners of a tetrahedron. Lone pairs do occupy space, but our description of the observed shape of the molecule refers to the positions of atoms only. Consequently, as shown in figure 6-22a on page 185 of your text or on the screen now, the molecular geometry of an ammonia molecule is that of a pyramid with a triangular base. The general VSEPR formula for molecules such as ammonia is AB3E, where E represents the unshared electron pair. A water molecule has 2 unshared electron pairs. It is an AB2E2 molecule. Here, the oxygen atom is at the center of a tetrahedron with 2 corners occupied by hydrogen atoms and 2 by the unshared pairs, as is shown in figure 6-22b. Again, VSEPR theory states that the lone pairs occupy space around the central atom, but the actual shape of the molecule is determined by the positions of the atoms only. In the case of water, this results in a bent or angular molecule. In figure 6-22b, note that the bond angles in ammonia and water are somewhat less than 109.5, the 109.5 degree bond angles of a perfectly tetrahedral molecule. These angles are smaller because the unshared electron pairs repel electrons more strongly than do bonding electron pairs. Table 6-5 on page 186 of your text or on the screen now also includes an example of the AB2E type molecule. This type of molecule results when a central atom forms 2 bonds and retains 1 unshared electron pair.
The atoms attached to a central atom spread out from each other as much as possible. But how does this model explain the geometries of molecules with non-bonding electron pairs? The nitrogen atom in an ammonia molecule has 1 non-bonding pair of electrons. These electrons also repel the adjacent atoms and do so even more strongly. The atoms, therefore, are pushed closer to one another. We can predict the geometries of molecules by considering the locations of all the electron pairs in the valence shell. Phosphorus trichloride, for example, is made up of a central phosphorus atom attached to 3 chlorine atoms by single bonds. Consulting the periodic table, we see that phosphorus has 2 valence electrons in s orbitals and 3 valence electrons in p orbitals. The chlorine atoms all have 7 valence electrons, 1 empty spot in one of their p orbitals. So each of the single p orbitals in phosphorus must be bonded with the single p orbitals in chlorine, leaving a lone pair of electrons on one side of phosphorus. According to our model, the geometry of phosphorus trichloride, therefore, is not trigonal planar, but rather trigonal pyramidal, with the chlorine atoms bent away from the lone electron pair.
Finally, in VSEPR theory, double and triple bonds are treated in the same way as single bonds, and polyatomic ions are treated similarly to molecules. Remember to consider all of the electron pairs present in any ion or molecule. Thus, Lewis structures in Table 6-5 can be used together to predict the shapes of polyatomic ions as well as molecules with double or triple bonds. At this point, you should be able to explain VSEPR theory and predict the shapes of molecules or polyatomic ions using VSEPR theory.